This video presents our survey, benchmarking distributional vector similarity measure by Cambria, Nobani, Pallucchini, and Mercorio. The question: how should you measure how similar two vectors are? Vector similarity is everywhere. Search engines use it to rank documents. Recommenders, chatbots, and plagiarism detectors use it too. The core step is always the same. Take two vectors, measure how close they are. A good measure improves everything built on top of it. But here is the problem. We reviewed 73 recent studies that use vector similarity. Only one out of 73 explain why it chose. Everyone else just used the default cosine similarity. So we are left with two gaps. We don't know which measure fit which rank. And we have no clear map of the options. Cosine similarity in one picture. Two embedding are two arrows from the region. Cosine ignore their lengths. Watch, the lengths change. The score does not. It only measures the angle. Arrow lined cosine near by 1. At 90 degrees is 0, unrelated. Beyond 90 degrees is negative. One number, direction only. Our survey does three things. A taxonomy with 15 measures organized in 5 families. A benchmark, every measure tested on 4 tasks and 6 embedding models. And a practical guidance, which measure to use task by tasks. How the survey was built? We start from 161 candidate vectors. Kept only high quality works on dense vectors. And ended with 73 studies and the 15 measures tested here. The 5 families were geometric, so Euclidean, Manhattan, Chebyshev, that are distance on a map. A set base, that is Jacquard, dice, Lin, that is how much do two sets overlap, and correlation, that is Pearson and Spearman. Do the vectors move together? Informatic theoretic is KL and JS, that is vector as probability distributions. And then inner product, so dot product and cosine. Cosine is just the dot product with the magnitude removed. So, same 2 points, but we have 3 distances. The Euclidean, the straight line. Manhattan, along the grid, always at the least as long. And Chebyshev. Only the largest gap counts. 3 honest answers. To how far? Now, treat the 2 vectors as probability distributions. The more they differ, the higher the divergence. KL is asymmetric. It depends on the reference. JS is symmetric and stay bounded. The test setup was this: 6 embedding models, including one trained with dot product instead of cosine. 4 datasets, 3 word similarity benchmarks, 1 shared preprocessing. All 15 measures on every combination. Four tasks, 4 definition of good. 1. Sentence similarity. So, do score match human judgment? Second one is KNN classification. Does it find the right neighborhood? And 3, the redundancy. Do measures really differ? 4 is structure. So, do Disney maps stay readable? The task 1 is sentence similarity average over the 6 models. The top is crowded. Cosine and Pearson at 81.3, Jacquard, Dice, and Spearman right behind. The interesting case is Lin, the 24.9 on average, almost useless, but on the top product model, Lin jumps to 73.6. Same measure, different model, opposite verdict. Lesson 1 is a measure is only good together with its model. Then, why? Keep the angle fixed. Stretch one vector. Cosine does not move. The dot product keeps growing. Magnitude leaks into the score. So, dot product only works on the model trained for it. The second task is KNN classification on movie reviews. So the ranking here flips. Manhattan and cosine lead at 0.73, Euclidean close behind. The task 1 winners, Pearson, Spearman, Jacquard, and Dice, drop to 0.40. Finding neighborhoods rewards through geometric distance. The second lesson is never carry a ranking from one task to another. The third task, are the measures redundant? Largely, yes. Cosine, Euclidean, Manhattan agree at 0.95 or more. Among near twins, just pick the cheapest. But Chebyshev around 0.8 and especially Lin see something different. Weak alone, useful as a second opinion. So, the fourth task, does the measure keep Disney maps readable? 3 groups emerge. The geometric family gives stable maps. KL and JS land close by. Chebyshev, dot products, and Lin drift off. Chebyshev comes last. 4 clustering and visualization stay geometric. The cheat sheet. Sentence similarity. Cosine, Pearson, or Spearman. But pick the cheapest. KNN and clustering use Manhattan or Euclidean. Need a different signal for an ensemble, Lin or Chebyshev. Always check that the measure matches the model's training objective. Cosine is always fine, often true, but not always. So, 3 open questions. What really drives measure selection? Needs, costs, or habit? Can one default work everywhere? Our evidence say no. And how do measures interact with the rest of the pipeline? The paper is Cambrian, Nobani, Pallucchini, and Mercurian. It was published at Expert System. Thank you so much for watching.